right? So we were saying these are the reasons why we need statistics in medicine. And as shown on the slide, these are the reasons that we just discussed. So the next big thing I want you all to get is data types, right? So types of data. Very easy, very simple. Quantitative, qualitative. That's the two big categories. Quantitative, qualitative. Qualitative, though, could be broken up into nominal and ordinal, and we'll see what that is. But if we take quantitative for now, quantitative essentially is something you can measure and count with a number, right? So if you can measure and count something with a number, it's quantitative. You could ask someone what's their weight, you could weigh them in kgs, the person is 76 kilograms. That is something quantitative. You could ask someone how much children you have, the person would say they have 3 kids. That is a number, it's something you could count. It's quantitative. Now, it could be continuous or discrete. The example I gave just now with the person weight is continuous because sometimes that could take on fractions. So if you had an accurate enough scale, you could weigh someone to the nearest 0.1 of a kilogram. You could say that they are 76.8 kgs. Discrete, though, cannot take on fractions. As things we could count, how much people in Group F, class of 2022, or how much children a person have, or how much times for the week a person on call. Those things they could count, but is discrete. They could only take on whole numbers. It's also quantitative, but it had the two types of quantitative data, continuous and discrete. So remember, quantitative, you could quantify it, a number, you could put a number to it. Whereas qualitative is things you can't put a number to exactly, but we'll see what qualitative data looks like. If you had to plot continuous data, though, continuous data essentially really may look something like this, or it may look something like this. So if I measure the weight of everyone in the class of 2022, I took all, how much, 250 of you all, weighed you all on a scale, and plotted it on the x-axis, I have the weight, and on the y-axis, I have the number of people who have that. If I plotted it, I would get a graph that may look like this, or may look like this. What's the difference between the two? This one is this what we call the symmetric bell-shaped curve, the normal distribution, and this one is what we call a skewed distribution, right? Because it's not symmetrical. It's it has a tail to it, right? Often, a lot of times when we plot continuous data, right, in medicine, HbA1c, patient age, people temperature, vital signs, a person weight, you're not going to get a symmetric bell-shaped curve. Often you get a skewed distribution looking like this, right? So just note that not all data is usually bell-shaped. But when you plot continuous data, you're only going to get something like this or this. We said quantitative measures with a number, and qualitative with a L could measure is nominal or ordinal. So what's nominal? Nominal comes from Latin for the word names. So it's names or categories. So if I ask everyone what county you're from in terms of address where you live, you would only belong to one of whatever it is, 7, 8 counties. If I ask everyone at this young stage what specialty you all hope to go into later on after you all finish medicine, people would say, well, I want to be a surgeon, I want to be a cardiologist, I want to do psych, I want to do internal med. You could only pick one out of several categories. So when it's categories, we call it nominal data, right? Or categorical data, you could also say. Now, if it's only 2 possibilities, we call it dichotomous or binary, right? So only 2 possibilities is dichotomous or binary. So you're looking at a study, a randomized controlled trial, I give the person medicine, it's either the person survive or they die, only 2 possibilities. If it's only 2 possibilities, we could describe it as categorical or nominal, but we go a step further and describe it as dichotomous or binary, as the words in di and bi suggest 2, right? So it's dichotomous or binary. When we drew that table and we worked out those things with relative risk, and we said, yes, the outcome was death, is either the person died or they did not die. To work out things like relative risk and relative risk reduction and all those things we worked out, the outcome have to be a binary outcome. Often in medicine, the outcomes we look at are not only binary or categorical. Ordinal data is categorical data, is data that you could think, well, it's separate categories, but you could put it in order. So if you could rank data and put it in order, all those separate categories, we describe it as ordinal, as it would suggest. Ordinal, you could put it in order, or we could describe it as ranked. If we ask a child, a little kiddie, have to go through some procedure, probably get an IV or something, and you ask the child, tell me how much this hurts. Pick one of these cartoons. It's 6 separate cartoons. It's 6 separate possibilities or categories the child could pick. But the question is, can you put this in order? Can you arrange them in some sort of order where one is last and one is first? That would make sense. Yes, you could. You could arrange it in order, and you could take the order and do this. Right? So from here, 6 separate categories, you have now put them in order. No hurt, hurts a little bit, hurts a little more, even more, whole lot, hurts worse. So they are separate categories, 6 categories, but you could rank them. Once you could rank them, we describe it not as nominal, but we describe it as ordinal. Right? So this is what ordinal data looks like. And if we had to say nominal or ordinal, and we had to show this data graphically, if I ask everyone in the class of 2022 what specialty you hope to go into, I know it might be a premature question, you guys not begin clinical years, but some people probably have minor field or specialty they may want to go into. That data might look something like this. I would show you a pie chart, and the pie chart would have all the possible specialties, and the percentages would be the percentages of students who choose that particular specialty. And I could show that in a pie chart or in a bar graph. Here, showing something with student grades, but again, it's either I get a grade A, B, C, D, F in this example here on the slide, and what percentage or proportion of people get this. So when we talk about nominal data or ordinal data, we're talking about percentages and frequencies, the amount of people or the proportion of people that choose something. So with that in mind, right, just to review, we say that everything we could measure in this measurable universe, anything we could measure could be put into 2 categories, quantitative, qualitative, and qualitative could be nominal or ordinal. So with that in mind, let's go through an example. Let's go through some examples and actually see if you all could figure this one out, right? So we're doing this by poll again, guys, right? Let me see if I could set up a poll to do this one. And we're doing this by poll. So I'll highlight the, I'll copy and paste one of them in the poll, and you all going to tell me if it is quantitative or if it is nominal or ordinal, right? So let me see how I'm doing this. Polling, multiple choice. All right, let me see. Quantitative, nominal, ordinal. Right, so let's pick the first one, right? So based on this, a Likert scale where we ask questions most of the time, sometime, a little of the time, rarely, what data type is it? Quantitative, nominal, or ordinal? You look at it, you ask, is this something you measure in categories or number? It's measured in categories. And the next question you ask, can you put those categories in order? And most people saying yes, you could put it in order. So yes, this is an example of ordinal. Most correct, Jane. Right? Ordinal. Right? So let's see the others. Dose of phenytoin a person gets. Right? Dose of phenytoin a person gets. And let's see. Dose phenytoin quantitative right. So what you all see? Dose of phenytoin a patient get. This is something you would measure in milligrams. Right? So it's either the person get 100 milligrams of phenytoin or the person get 1500 milligrams of phenytoin is something you could quantify, and the majority of people are saying yes, quantitative. So that was quantitative, right? So that was a good example of a quantitative variable. I don't know if you all might know what an APGAR score is, but an APGAR score essentially is essentially something that you get done at birth. That's right, Annalise. And an APGAR score usually ranges between what numbers? If you're all familiar with it. 0 to 10, most correct. So 0 to 10 means 0 means the baby is really, really not active, not breathing, little activity, and 10 means the baby is fully active, alert, moving, has good movements, good respiratory rates, that kind of thing. So it could be 0, 1, 2, 3, 4, 5, and it's an arbitrary scoring that we generally give. So the question is, what kind of data would this be? All right, what kind of data would this be? So this one might be a kind of tough one because based on the definition I just gave of an APGAR score, you would tend to think, well, it's numbers, but it's numbers of what? The thing about the APGAR score is something that is a random score that's arbitrarily assigned to the patient. And what we would usually say is a child with an APGAR score 8 is better than an APGAR score 7. But when I say the APGAR score is 7 or 8, is 8 what or 7 what? It's just 8 points. So most people saying it is ordinal, and ordinal actually is the correct answer. Some scores we use in medicine are not quantitative, is more ordinal. And a question was asked, is it linked to intelligence? So yes, I actually just helped one of the DM pediatric people analyze a data set, and they tried to see if there was an association between APGAR score and developmental delay and milestones later on in life. And we found that there was an association. So APGAR scores at birth could be linked to things like developmental delays in children and pediatrics. When you go to a pediatric rotation, you would soon learn that, right? So that is what it is, right? So APGAR score is ordinal, right? APGAR score is ordinal. Next thing, if we record a person's blood pressure and we record it under several categories, suppose we record it under the categories that I have here on this slide. Quantitative, ordinal, nominal. What you all think about this one? So recorded people's blood pressure. You say the person either was normotensive, pre-hypertensive, stage 1 hypertension, or stage 2 hypertension. That is how you recorded the blood pressure. You look at it. Is it categories or not? Yes, it is categories. Can you put the categories in order? Yes, you could put it in order. So if you could put the categories in order, then it would be ordinal. I see people have changed their mind from nominal to ordinal, which is the correct change. So yes, it is ordinal. This would be an example of an ordinal variable, right? So this would be ordinal. So I just gave some examples of the ones we do. The others on the slide, I'll just call them out. So systolic blood pressure, if you actually measure the blood pressure, 156 millimeters of mercury, that would be quantitative. If a baby was born either through vaginal delivery or cesarean delivery, only 2 ways the baby come out, we say only 2 possibilities. That would be an example of a nominal variable because there's only 2 possibilities. Specifically, we could say this one is dichotomous or binary, right? So there's nominal. BMI is a number, it has units, kgs per meter squared. So BMI would be an example of a quantitative variable. Cancer grade, the grade of cancer either was grade 1, grade 2, grade 3, grade 4. 4 separate grades, but we could put them in order. Grade 4 cancer behaves much more worse than grade 3 cancer. If you have to pick one to get, you would choose grade 1 because that is the least invasive one. So cancer grade would be ordinal. And blood group. Blood group would be either A, B or O. If you throw in resource, you get 8 possibilities. You can't put that in order. You can't say A before B or AB before O. So it's separate categories. So that would be an example of nominal variables. Blood group would be a nominal variable, right? So in a nutshell, those are the different types of data that we could measure generally, right? So yes, perfect. So that's the big thing I wanted to get. The other thing in statistics, I am no statistician. I do a lot of it as part of my work in terms of analyzing data sets and doing lots of research, but I'm no statistician. But what I would say, when we do statistics, we look at different aspects of it. We look at descriptive statistics, and we look at inferential statistics. Descriptive statistics means we just try to describe a sample, describe a group of people. Inferential statistics means we try to make an inference from the sample to the population. So we'll see what descriptive statistics is. We actually have been looking at inferential statistics without you all realizing it. So what inferential statistics is really when we make generalizable comments from a group of people in research to the population. So when we actually say the hazard ratio was this, and this was the confidence interval, what that actually is an inferential statistic. We're saying something, the hazard ratio was 1.2 in the group of people we study, but we're saying the hazard ratio was within this range for the population of patients. That's really what we're saying. So a confidence interval actually is an inferential statistic, just to put it into perspective. So here, what we're seeing? We're seeing descriptive statistics, and these are the measures: mode, median, and mean. These are measures of central tendency, and they are also measures of range, variance, and standard deviation, what we call variation. So you all know these measures. These measures are mean, mode, and median. And this is an example of mean. I want you all from this example to tell me what is the mode and what is the median. Take a minute and tell me what's the mode and median here in this set. Perfect. So I've seen some people here saying the mode was 2, and people saying the median was 3. So from this set of numbers, the first thing you have to decide is put them in order. So remember, to determine median, you have to put them in order. So if you put them in order, you get 2, 2, 3, 6, 9. So the median was the middle number. So in this case, the median is 3. Remember, you have to put them in order. Yes, Annalise. In this case, the mode is the most frequent number. So the mode was 2. 2 is the most frequent number. And as shown on this slide, the average is 4.4. So look at these different measures. One saying the mean is 4.4, one saying the median is 3, and one saying the mode is 2. So which one you look at? Which one you believe? Which one you go with? Well, all these measures, mean, median, and mode, tell us where people are close to the middle. They give us an idea where people are close to the middle, but they don't tell us variation. So that's the limitation with mode, median, and mean. They give an idea where people are close to the middle. Looking at these set of numbers again, you would get, well, you wouldn't think that someone was a 9. The only way we would figure that out is if we ask you to report on things and other measures like the range. So if I ask you what was the range here, you could say it ranged from 1 to 9. That's what you would say. In terms of the other measures of standard deviation, we use this one called variance and standard deviation. And variance and standard deviation, more or less, tells us how much people spread out in the sample. So when we talk about descriptive statistics, these are the measures that we generally use. You would see them reported in studies, and they give an idea as to where people lie close to the middle and how much people spread out on average, apart from the average on either sides, right? So these are what we call descriptive statistics. So I just went through those quickly. One of the things you need to know in research that we like to do is this thing called sampling. And there are different types of samples. One of the ways we could sample is random sampling. We could do systematic sampling, convenient sampling, cluster sampling, and stratified sampling. Wouldn't spend too much time on it. What I would say here is the most or the best type or form of sampling really is to take a random sample. The reason why we like to use a random sample is because a random sample often is most representative. If I had to do a study on the class of 2022 and I wanted to select, let me just say, 40 students, I would pick a random sample of 40 students from the entire list that we have of the whole class. If you pick a random sample, the idea is the 40 students you get going to be more representative compared to if you picked a convenient sample. A convenient sample would be something like, all right, you just walk into a classroom. If we were doing this in a classroom in our family medicine unit, if I just walk into the classroom and group F is there and I say, all right, I'm going to pick these 36 or 39 students or whatnot in group F, and I'm going to give them a survey to fill. The survey you all fill may not necessarily be representative of the whole class because I picked a group of people by convenience. So in medicine, often what we use are convenient samples, but they're not always very representative, but they're easy to get. A systematic sample would be not random, not convenience, but there's a system to it, there's a predictability to it. So you could actually say, well, I'm going to pick people systematically. And how we're going to do it, I'm going to pick the list of everyone, and I'm going to pick every 6 persons. So let me just say a class had 240 people. I pick every 6 persons. I would get 40 people. Number 1, number 6, number 12, number 18, and keep going. It's a systematic sample because it kind of could predict who's going to get picked. It's not random, but it's not convenient, but it's systematic. That'll be an example of a systematic sampling, which we sometimes use in research. Cluster sampling is what they do surveys in the whole of Trinidad and Tobago. So when Central Statistical Office do a census, so a nationwide survey, they usually select geographic areas in Trinidad called enumeration districts. They have these maps and they group the maps into clusters. So when you have to do a sample of a whole big nation, a huge big population, what would often be done would be cluster sampling. And the last thing I'll say, stratified sampling is the type of sampling technique we use when you realize that there are different groups within your big group. The example I usually give with this is Tobago students. So we know that Tobago students are probably the minority in any given class, in any given MBBS class. In any class, usually there are a handful of them, usually maybe anywhere between 5 and 15 Tobago people out of a class of probably 250. So they are a minority. So what happens when there are minority groups or small subgroups within a population? If you pick random sampling, you could miss them. So if we were to randomly pick 40 people, there's a possibility we may not get representation from our Tobago students. So stratified sampling says no. Stratified sampling says we realize that there are 2 strata in class. We have a Trinidad group, the majority, but we also have a Tobago group. And if you wanted to do research and get the perception of medical students towards something, and you want to include Tobago people, you have to do what we call stratified sampling. You have to pick a group of people from the Tobago group, that strata, and then pick a group of people from the Trinidad group, that bigger strata. So that's stratified sampling. So in a nutshell, those are the different types of sampling. I usually mention it because sometimes questions pop up, old MBBS questions pop up about it when people do final MBBS, so sometimes people have questions about it for research. But you should just know of the terms, right? The next big thing I want to talk about is how we'll know which statistical test to choose. It depends on what we're trying to accomplish. Are we trying to compare 2 or more separate groups? Are we trying to compare a placebo group with a Plaquenil or hydroxychloroquine group? Or is the data matched? Matched data means usually like a before and after. Were a group of people in pain, and then we give them a pain medicine, and then we measure their pain before they got the medicine and measure their pain after the medicine. If we did that for 10 patients, we would have 20 readings, 2 readings per each patient, a before and after. We call that matched data. Or are we trying to make a prediction? If you tell me the clerkship grades for year 5 medical students, and I predict if they would be successful at final FAs and BBS based on the clerkship grades. Can we make a prediction like that? So you could actually look at those things as in research and actually try to figure out if you could actually do those things. That is what statistics allow you to do. The first test is only 4 I'm going to mention. The first basic test you all should know about is actually named after you guys. It's called the independent sample t-test or the student's t-test. And the student's t-test does one simple thing. It asks, is there a difference in averages or is there a difference in means? So this test could be appealing because we often want to compare averages. Suppose there are 2 health centers, the example on the slide, Health Center A and Health Center B. And suppose someone says, well, I think my patients in my health center have better sugar control compared to the patients in another health center B. I think the doctors do a better job in controlling people's sugar in my clinic compared to your clinic. We could actually test that. We could actually go and measure a group of people, pick 10 random people in Health Center A. And here you're seeing the 10 measurements of HbA1c as a percent from Health Center A. And what we could do with these numbers, we could work out the mean, we could work out the median, we could work out the mode. But what are we working out here? We're working out the mean or the average. We could work out the mean of these numbers, add them up, divide by 10, and we could do the same thing for Health Center B. When we do that, this is what we get. We get the average HbA1c in Health Center A was 6.79%. And the average HbA1c in Health Center B was 7.19%. Obviously, they are different. But remember, anytime we see differences in 2 groups, what we need? We need a p-value to tell us if the observed differences were due to chance. So what's the interpretation here? We just went through this in the last lecture. The p-value for this, when you do the t-test, it gives you an output, and it gives you this thing called a t-value. You don't have to worry about that, but it gives you a p-value. Probability value. The p-value is 0.0699. We could round it off, 0.07. No statistical significance. In other words, the 7.19 wasn't significantly more than 6.79. We could conclude that the difference in both average HbA1cs between the groups are not significant. In other words, the HbA1c groups in both clinics are the same. Right? So this is an example. So the p-values we spoke about in the last lecture actually comes from statistical tests. You don't have to be concerned with how it's calculated. Software and statistical calculators calculate it. All you guys have to be concerned about is the interpretation. All right? Again, the students' t-test, you would think, well, we could use this a lot. We could compare averages. We could compare the average grades between groups of students. We could give you all an exam and compare the average grade in group F with the average grade in group D. We could compare the average performance or the average grades between years, between class of 2022 and compared to class of 2021. But the students' t-test have a few assumptions and limitations. It assumes a few things. It assumes that your data is quantitative and normally distributed. Remember, I showed that bell-shaped curve. Often in medicine, lots of things we measure don't follow that normal bell-shaped curve. It's skewed. And if the data is skewed, you actually cannot do the independent sample t-test. You have to do another test. It also assumes the variances are equal. Variances is one of the spreads of variation in groups. If the variances in 2 groups are not similar, you can't do the student t-test. And it assumes the observations are independent. They are not matched. You don't have to be concerned with these assumptions. No one going to ask you this for no exam at your level. You just need to know that all statistical tests have assumptions and limitations. And if the assumptions not met, you should not do the statistical test. You should choose another test. If you ask a statistician, they're usually able to advise you what is the test you should choose. Second test you should know about, right? Remember, so we're only going to talk about 4, and that would be it. This one you all might have been familiar with from the research you all did in year 2. It's called the chi-square test. Remember the data types? We say it could be quantitative or qualitative. Chi-square test tells us or answers the question, is there an association between 2 or more categorical or qualitative variables? That's really what it does. If you want to compare the admission rate, the amount of people that get admitted or the percentage of people that get admitted in Mount Hope Hospital, and you want to compare that with the proportion of people that gets admitted in Port of Spain General Hospital, you could use the chi-square test to do something like that. Which hospital they belong to, Port of Spain or Mount Hope, that's categorical. If a patient gets admitted or not, what type of data type that is also categorical. Once you're comparing categorical by categorical data, you could do the chi-square test. This is an example for some research I actually did. This was some research I did a few years ago with a group of medical students. We're actually trying to publish this paper now. We looked at joint pain in Trinidad by doing some research on patients visiting the clinics, the health centers, and we asked them questions like if they got joint pain in the last 6 months. So either had joint pain or you didn't have joint pain. Yes or no, so that's categorical, it's nominal, it's dichotomous. And then we noted a whole set of factors, one of them, of course, being gender. So what we found is that the females, when we actually measured the persons, it was probably about 300 plus people we measured. You're able to draw this table that you see in here, or this kind of data shown here on this slide, you're able to compile it and put it like this. So here we see 148 females say yes, they had joint pain compared to 88. But you can't just look at the actual numbers. You have to calculate the percentages and the proportions. So to do that, you enter the information in a software package like SPSS, and what it does, it gives you this output. So look at this output. Looking at this output, you see in a whole set of Greek. All you have to do is be able to look and say, look, this was a chi-square test, all right? And all you have to do is look at this thing, significance, which is really the p-value, and 0.13 is the p-value. How we interpret a p-value as 0.13 again? What you all would say, the p-value is 0.13. Significant or not? P 0.13. We did that a long time ago, about an hour and a half this morning or an hour ago. If the P is less than 0.05, we say it is significant. So in this example, there was a significant association between gender and joint pain. And actually in this example, women were more likely to complain of joint pain compared to men. So this is practically how we would use statistics to answer these kind of questions. So now you might wonder, well, why is that the case? Chi-square testing has limitations. Again, the thing about limitations for chi-square testing is ideally it works well when you have big samples of people. If you use chi-square testing for small groups of people, 10, 20 people, it doesn't work too well. You have to use other statistical tests. And it have other limitations, which I wouldn't go into, and you don't need to know. You just need to know that all statistical tests have certain assumptions. The third statistical test, right? So 3 out of 4. Is this one called correlation. And correlation asks a simple question. Is there a relationship between two quantitative variables? Is there a relationship between two quantitative variables? That's what correlation tries to answer. So is there an association between a person's muscle mass and their creatinine level? Is there an association between that? We know that the more muscle mass you have, the higher your creatinine level when you check and do a blood test. So we would say that both these are positively correlated. In other words, the bigger the muscle mass, the more creatinine you have in the blood. How about minutes spent exercise and rest and heart rate? Where's the association here? The more exercise you spend doing weekly, especially aerobics, the lower your rest and heart rate tend to be. So the higher minutes spent exercise, the lower your pulse rate. So we say both of these are correlated, but we say they are negatively correlated. And that's what correlation tries to do. This is how it's reported. It's reported as something called R, which is the correlation coefficient. And R lies between -1 and +1. If your correlation coefficient at +1, it means there's a perfect positive correlation. If the correlation coefficient is -1, then we say it's a perfect negative correlation. As one goes up, the other one goes down. And if the correlation coefficient is 0, it means there is no correlation at all. So anytime you have to interpret correlation, you would see R, a value for R, and you would see a p-value. You're going to see two things. And again, of course, I'll give you all an example. Again, from the same research we did looking at joint pain and arthritis in Trinidad and patients attending primary care clinics, we looked at correlation between quality of life domain. So we measure different aspects of quality of life, their mobility, their activities, the general health perception, the mental function. And we actually tried to see if there's a correlation between these measures, which people got a score for each one, a continuous score. And we actually tried to see if it was associated or correlated with the severity of pain. We measured pain on average, pain at its worst, and we measured actually the duration of joint pain. And I highlighted the ones that I wanted to speak about with you all. The one in red shows your mobility and the severity of pain was related. The p-value was 0.001, so we know it's significant, and the correlation was plus 0.34. So that means, if we go back to this, 0.3 means there's a weak, relatively weak association, but it was an association that was significant between mobility and the severity of pain, and it was significant. How about leisure and social activities? Leisure and social activities, we see it was negatively correlated, 0.13. 0.13 for R means it's actually a very weak association, but it's a very weak association that was significant. But because R is negative, it means it was a negative association. That is what it means. That means the longer or the more duration you had of your joint pain, the less leisure and social activities you will be able to do. As one went up, the other one went down. And the third example on the slide, the one I highlight down here in green, is was there an association between mental function and severity of pain on average? Here we say R was 0.09. That again, 0.09 is very weak, but was it significant? No. The p-value was 0.164, and we all know if the p-value is more than 0.05, it's not significant. If it's less than 0.05, it's significant. Again, what I want you all to really get here from this slide is just the interpretation. It's really the interpretation of p-values, repetition, right? It helps. And the last statistical test we'll talk about today is this one called regression. Regression tries to make a prediction. I gave some examples about it earlier on. If I know the grades of students in 5th year in the clerkships, can I predict the outcome of those students at MBBS exam a year later? Regression allows us to answer questions like that. So if X is the clerkship grades and Y is if they pass or fail MBBS, can we make a prediction? We could actually do that and work those things out by looking at data from past students and groups. In this case, the dependent variable is what we call the outcome. In this case, it will be if you pass or fail final MBBS. And the independent variable is what we look at as the predictor or the risk factors. In this case, it would be year 5 clerkship student grades. So regression tries to answer that question. So regression is about prediction. Can we predict an outcome, a dependent variable, based on an independent variable? And regression could be different things. Here, regression could be having an MI and cholesterol level. So in this case, having an MI would be the dependent variable, that's the outcome, and cholesterol would be the independent variable. If I tell you a person cholesterol level, can we predict if they will get a heart attack or not? Having an MI, yes or no, you either have it or not. That's dichotomous, it's binary, it's nominal. Cholesterol level could be continuous or quantitative. Blood glucose level and visual acuity. Blood glucose level is the independent variable, the risk factor. Visual acuity is the dependent variable. When a person's sugar goes up, it could cause their vision to be blurry. When people go to the optometrist and they have blurred vision, they can't even read the chart, they check the sugar, they see a high reading, they send them by a doctor, they sometimes end up by me. They say, hey, doc, I went to check vision and I'm known to be diabetic, but my vision was blurry and they said my sugar random when the check was 320. They say I need to see a doctor. So blood glucose level could predict vision. QT interval and sudden death. QT interval is something that we measure on an ECG. It's something that's measured in milliseconds, so it's a quantitative variable. Sudden death, the person either had sudden death or not. That would be a dichotomous outcome. That would be the dependent. Age, smoking, HbA1c, and stroke. This might seem confusing, but here in this case, stroke is the outcome. Stroke is the dependent variable, and all the rest are the independent variables or the risk factors. Statin dose and liver enzymes, you all may know when we give people statins, it might raise their AST and ALT. In this case, liver enzymes is the outcome or the dependent variable, and statin dose is the risk factor, independent variable. Right, so that's just examples of how we could use regression and what could be the outcome and on what would be the predictor. So regression, there are different types of regression. Again, all these extras, you don't need to know this, but you'll see this when you read a medical paper. If the outcome is continuous, we do what we call linear regression. So can I predict a person's cholesterol level in the blood based on how much sugar they eat every day, how much fatty foods they eat, how much red meats they eat? We could do a regression analysis to work out that. Take a group of people, measure the diet, measure everyone's cholesterol. If the outcome we're looking at is something like the cholesterol level, then we would do what we call linear regression. We're trying to predict an outcome that is quantitative. If, however, we're trying to predict an outcome that the person either responded to medicines or did not respond, the person either survived or died, there's only two possibilities. If we're trying to predict an outcome that's binary or dichotomous, the type of regression we do is something called logistic regression. Right? So those are the two popular types of regression you would see reported in the literature when you read medical papers. There are others as well, but I wouldn't talk about those. It's kind of beyond the scope of this class. This is an example, how we interpret it. So if you look at the slide, you would see it's logistic regression of risk factors for heart disease and multivariate analysis. What does all this Greek mean? Logistic regression. We're trying to make a prediction of something. That's what regression allows us to do. Can we predict what? Coronary heart disease, CHD. Can we predict if a person gets CHD or not? It's logistic regression, so that tells us the outcome was dichotomous or binary, meaning it's either the person had CHD or they didn't have CHD. Multivariate analysis, what this big word simply means is there were multiple independent variables or multiple factors or risk factors, and these are all the factors here. So how we interpret it, the interpretation is in this red box. You all know how to interpret this actually already, because what we're seeing is a p-value, and what we're seeing are odds ratios. So if we look at the p-values here, we can see all of them are less than 0.05. Age, hypertension, LDL, HDL, they are all significantly associated with the outcome of CHD. Look at diabetes in this example, in this research, it was 0.057. So that's more than 0.05. So you would say in this data set, diabetes was not associated with CHD in this bit of research. Of course, we know in reality it is. Diabetes itself is a big risk factor for people getting heart attacks and strokes, even if the cholesterol is perfect, even if they're not old, even if the HDL is high, even if they don't have hypertension. In real life, we know diabetes is a big risk factor for getting heart disease. But in this analysis that was done from a particular research study, they did not find an association. So in this case, looking at the p-values, it would say, well, diabetes wasn't associated, but the rest were associated. Age was associated, hypertension, LDL, HDL, which we know from our knowledge about these risk factors. What the odds ratios tell us though, the odds ratios tell us the direction of the association. So if we glance odds ratios, what we see, the odds ratios and the 95% confidence interval, remember that? All we have to do is look at the range and ask, does it include the value 1? 1.8, 2.7, does it include 1? No, statistically significant. Age is significantly associated with an increased odds of CHD. Hypertension, 1.38 to 2.69. Does this include 1? No. Again, statistically significant. The odds ratio is more than 1. So that means if a person has hypertension, they're more likely to get CHD. Same for LDL, 1.3 to 1.8. It excludes the value 1. Therefore, it is statistically significant. LDL increases the risk of CHD. HDL, 0.57 to 0.82. This excludes the value 1, so it is significant, but the odds ratio in this case is less than 1. So what this means, the greater your HDL, your odds of heart disease goes up by a factor of 0.68 as a fraction is less than 1. And we said before, earlier this morning, if the odds ratio, the relative risk, the hazards ratio is less than 1 and it's significant, it means that factor is actually protective. So it means when the HDL goes up, heart disease goes down. It gets less. Is it significant? Yes, because 0.5 to 0.8 excludes the value 1, but the association is inversely related. How about diabetes? 0.98 to 2.0. Does this include the value 1? Yes, it does. So in this case, what it means, diabetes was not associated with increased risk of heart disease. Again, in this data, in this example, for the purposes of this example only, that is what this found. I'll just pause there and again go back to the chat to see if that interpretation lost anyone. And if you're okay with that interpretation, if you all understand it, is more or less the same thing we did when we spoke about confidence intervals in the last presentation. But again, for repetition, I want to just make sure you all got the interpretation and no one is confused about it. All right, so any questions about that? Make sense? All right, Catherine, yeah, makes sense. What you would also notice is generally the p-values and the odds ratios agree. They say the same thing. So if you notice for age, hypertension, LDL, and HDL, the p-values were all significant and the confidence intervals were all significant. If you notice for diabetes, the p-value was not significant and the confidence interval was also not significant. And generally that is the rule. Where you see both p-values and confidence intervals presented, they generally gel, they generally are congruent, they say the same thing, right? So in wrapping up, what I just have to say in conclusion is two things really. We spoke about p-values. I think by now we're confident that you guys know how to interpret them. If it's less than 0.5, 0.05, you all would say significant. But to add to what you already learned this morning, think about two questions. If you see a significant p-value, sometimes people or medical researchers use the wrong statistical test. Today we only spoke on, I only mentioned 4 statistical tests, but there are many other statistical tests that are used in literature. And what I highlighted with the statistical tests that we spoke about is sometimes you cannot use them. Sometimes researchers inappropriately use the statistical tests we mentioned because it gives a favorable or a p-value less than 0.05. In other words, they ratch. The ideal thing is to use the correct test. So anytime you see a small p-value, ask, all right, well, statistically significant. I wonder if these people did the correct statistics. The other question I want you to ask is p 0.01. Yeah, that's significant, but is it clinically significant? So what's the difference between statistical and clinical significance? We'll highlight that on the next slide. If you see a p-value more than 0.05, ask yourself, well, it's not significant. So if I tell you the p-value was 0.13, you can say, well, no difference really. But the other question I wanted to think about is, did the study have enough people? Sometimes in reality, a treatment makes a difference, but you come and you conduct a study, a randomized controlled trial, and your trial have 40 people in it, 20 people in each arm. And your study say, well, I didn't see a statistically significant difference. Your study could have found that there was no significant differences simply because it didn't have enough people in it. If you did the same study but included 400 people, if the treatment really working, sometimes you would see that, hey, now this treatment's actually working, it's making a difference. So you always have to keep in mind sample sizes. Again, that's beyond the scope of this presentation, but always keep in mind sometimes if a study don't have enough people in it, sometimes you can't get the conclusions you hope to. So this slide kind of nicely highlights the difference between statistical and clinical significance. Look at the examples on the left. A drug reduces blood pressure by 1 millimeter mercury, p 0.001. Is it statistically significant? Yes, p less than 0.05. Is it clinically significant? Probably not. Because if a drug lowers your blood pressure by 1 millimeter of mercury, that's probably not going to save people from heart attacks and strokes and stop them from dying, the reason we treat hypertension. So, I mean, here you see in the conclusion here, it's statistically significant, but I probably would not prescribe this treatment to my patient because it's not going to really make the blood pressure drop by an amount that I consider clinically significant. A drug reduces blood pressure by 25 millimeters of mercury, p-value 0.02. Here, it is not statistically significant. The drop was clinically significant, a drop by 25 millimeters of mercury, but the p-value here of 0.2 tells us that the chance that it reduced your blood pressure by 25 millimeters of mercury, there was a high possibility that that drop was due to chance. So in this case, again, I would not prescribe this drug because although it apparently reducing blood pressure, the p-value tells us it's not statistically significantly doing so. Look at the third example. A drug reduces blood pressure by 25 millimeters of mercury and the p-value is 0.001. Is it statistically significant? Yes. Is it clinically significant? I would also say yes, because the p-value is less than 0.05. And I would say I would pick this drug. I would pick this drug over the drugs in the other two scenarios any day, because not only is it statistically significant, it's also clinically significant. So this raises the question then that you may ask, how we know if it's clinically significant? And the answer to that question is it really depends on what it is you're looking at. In the case of blood pressure, studies have shown over many, many decades and years that if you drop a person's blood pressure, if they're hypertensive, if you reduce it by as little as 5 millimeters of mercury, it could translate into outcomes where the person is less likely to die and develop heart failure and kidney failure and adverse outcomes. So the clinically significant drop in blood pressure we know and we use in practice in medicine is 5 millimeters of mercury. So although this first study significantly reduced blood pressure, it didn't reduce it by an amount that we consider clinically relevant. So clinical significance is somewhat of a subjective judgment call. You have to be aware of what it is you're looking at. You have to be aware of what the literature shows and has shown to be clinically significant, right? So I think this slide was a good slide in terms of highlighting the differences between the two. I added this slide to the presentation last night and updated the presentation last night. If people downloaded the older version of the presentation before yesterday, this is the updated version because I thought this graphic, which I found kind of very nicely highlights the importance and the difference between statistical and clinical significance. So in summary, what we spoke about today, essentially we said statistics, why we use it. We spoke about the different types of data. Remember, quantitative, nominal, ordinal. We saw some commonly used statistical tests that we could use. And we spoke a bit about interpretation, how we interpret these findings. And that concludes the statistical